in today's lecture, we'll be discussing how we can track a time varying function instead of a reference signal which is zero. So in our previous example, we designed the regulator properly. In today's lecture, we'll be designing tracking controller where we will track a time varying function as a reference signal. We'll go with the first the mathematical derivations of the controller. Then we'll take same example what we had in the last lecture, but we'll track a time varying function here. But basically the desired dynamics to be tracked. So let's start the lecture. Main control design for tracking a time varying function, and also we have MATLAB simulation for validation of the concept. So let's start the lecture. So here we are assuming the desired dynamics to be tracked. Desired dynamics to be tracked xt dot equal to axt. So here we are assuming all the eigenvalues of, sorry, it is AD. All the eigenvalues of AD matrix should be negative. So it is very stable function. So here we are going to track the xt dynamics. Okay. And the natural dynamics in state space LTI form, we are going to consider, we already had before the system basically x dot equal to ax plus u plus f xn. So here, if you look the closed loop control block diagram, this is the summing point, and here we are having the controller. Controller is here, control block, which actually try to find the control gain. So controller, and the controller output goes to the plant to be controlled. Here, and this is the output the plant X. And we are having here, instead of zero reference signal, we are going to track a time varying function xt, and this is feedback. So now we can find the error dynamics. So here, if you write E equal to, for this case, xt minus x, right? So now error dynamics you can write. So your plant, you can see aircraft system. And also we are having noise xn in the system as well. So error dynamics you can write. Let's write E equal to xt minus x, and error dynamics immediately equal to xt dot minus x dot. And from this we can write AD xt minus AX minus BU minus F XN, and this is we can write, and here we are doing some manipulation here, which ADX XT, sorry, should be XT, and minus AX minus BU FXN AXT minus AXT. To make the simple in closed loop form, that's why we have one term added and subtracted here. So now we can write A xt minus x plus xt AD minus A, we can write minus BU minus AXN. Okay. And also you can write A, this is nothing but E, right? This part. So instead of this xt minus f, we can write E here, and plus AD minus A xt minus bu f xn. Okay. So here, but for the but in the previous lecture we had since xt was 0 in the previous lecture, so u can be formed as minus kx. Why? Because generally u we define kx, right? Ke. So since xt is 0, so we can write k minus x, so minus k. But in this case, we can't write in this form. We have to write equal to, so equal to, we have to write Ke minus Kd xt minus Kn xn. This is how the control structure should be for this particular, for this, in this course, for the tracking control. Yes. So we can write in this form. So now we can come back here. So here we can write A plus AD minus xt, and in place of u we can write Ke minus xt and we can write Kd xt minus Kn xn, right, and minus fxn. And from this, we can write A plus AD minus A xt minus BKE plus BKD xt plus BKN xn minus fxn. Or we can write A minus BKE. So we can use this term and this term. We can write this term, and plus we can write AD minus A, sorry, plus BKD xt plus BKN minus f xn. So if you notice here, very interesting equation we have. So in all these terms, we have some form of matrices. This is one matrix, this is one matrix, this is one matrix. If all the eigenvalues of these matrices are negative, then we can say as t tends to infinity, E goes to 0, right? If all the eigenvalues of the individual, all these matrices are negative. So now let's see how we can do it. So let us find some condition on KD and KN, so that anyways we have to design the controller for this, but the critical part is this part and this part, right? So let's start. Let me write some stuff here. At steady state, the error either reduced to 0 or may yield some small value, right? So in this case, or small value means it can go some constant value. That steady state means some constant value, right? So in that case, the derivative of E dot will be 0, we can write. So at steady state, we can write at steady state, we can write 0 equal to A minus BK. So at steady state E is going to zero, either zero or can go to some small value. So in that case, if you consider small value, we can write ESS some small value plus AD minus A plus BKD XD SS also desired dynamics goes some steady state value plus BKN minus A xn also goes to some steady state value. So now, if you simplify this expression, we can write from this expression ESS equal to A minus BK inverse A minus BKD AD XDSS plus F minus BKN XNSS. You can write, right? So you see, in state feedback control, what you have learned, we can design this part, right? This part we can, if you can manipulate K matrix, we can make the eigenvalues of the overall matrix to negative. So in that case, it is stable. Now, the only other condition ESS can be made zero when this part and this part are going to zero. That is very important because this is not equal to zero. A minus BK not going to zero. Otherwise, this will not satisfy. Inverse will not possible. So even it is practically we have done right in the previous questions that A minus BK always invertible. So in this case, we can write since ACL, this is nothing but ACL, right? This is nothing but ACL. So we can write here ACL. So now ACL equal to A minus BK not equal to zero since eigen values are in left half plane. Now for ESS to be zero, the only conditions are A minus B AD minus AD equal to zero and F minus BKN equal to zero. So from this condition, so we are need to find KD and KN in such a way that ESS goes to zero. So we can write. So we need to find KD and KN in such a way that this will yield ESS equal to zero. We can write. So in this case, we can write KD equal to B inverse. From this two equation we can write. From this equation we can write B inverse A minus AD and KN equal to B inverse F. So these are the mathematical foundation to design the controller if you need to track a time varying function. If you need to track a time varying function. This is the procedure you need to follow. Now let's move to the example part. Example. So here we are going to consider same example, what we have done. So I will take this. This is the example we had in the last lecture. The same example I'm going to consider here. But here we can modify a little bit. So this part we can modify this right up. We can modify design a controller that makes aircraft track a target or desired dynamics such that we can write here. So what are the we had state, we had one state was normal acceleration, pitch rate, and elevator deflection, right? So which can follow the desired dynamics here. So we can write a desired and Q desired and elevator desired. Okay. This is elevator deflection. This is elevator deflection. Okay. So we can form the desired dot. Okay. And the matrix, AD matrix, we are assuming 10.1, 335, 150, 0.1, minus 1.1, minus 21, 0, 0, minus 8. And we have AD here, UD here, and UD here. So the desired dynamics. And one thing, please notice, remember that the dimension of the system matrix of the desired dynamics should be same as original system dynamics. This is very important. Otherwise, we can't take the error between this. This is we are considering based on that assumption, right? So now we'll solve this problem. So let us first analyze AD and find the natural frequency, damping ratio, and poles in MATLAB. Okay. So for that, we can find, so here, this is the AD matrix. This is our AD matrix, right? So if you use in MATLAB, damp AD, if you enter it, so output will be omega n, damping ratio, and poles. So it is 10.471 minus 10.4 and 0.721 minus 0.72. This is 8, 1, minus 8. So this is the output we are getting. But if you notice here carefully, all desired poles are on the left-hand side. So we can say this system is stable, right? Now our next part is, so now we'll design the controller for the first part. So now we are going to start to work on this part first, this part. Okay. So here we are going to consider the desired pole to be, let's assume the same desired pole what is given in the example here. The same desired pole we are going to consider, this desired pole. So desired pole given to us Bezier folds are S equal to -1, S equal to -1 plus minus I, right? Now, if you remember, we can use the place command to get the control gain for this particular Bezier folds we had in the previous example. Please go back to it. Go to the lecture, last lecture. We had K equal to 0.006, 0.006 minus 0.0244 and minus 0.8519, right? And also we had ACL and KM also we have found in the last lecture. ACL we had the closed loop or the augmented matrix we had minus 1.526 4336 28.28 0.22 minus 1.4 minus 32 minus 0.008 0.34 and minus 0.07, right? And also we had Kn. Please refer to the last lecture. We had all these values because we had the same example, but it was regulated problem. Minus 0.02 divided by 272 minus 0.1 272. So these are the values we had obtained in the last lecture. Now, here the challenging part is the last, this part, right? This is the one we have to work on now, this part. So let's start how we can work on that. So here we need to find feed forward gain matrix. Why feed forward? Because if you notice, the controller was designed here. In the controller, one of the parameter we had minus KDXT. So this part we can call feed forward control part, because the controller depends on the Bezier dynamics, XD. So here we can, let's assume the KD matrix. KD matrix, we are assuming KD1, KD2, KD3. Okay. And we can find the matrix A minus. Maybe you find difficulty, but we have MATLAB problem for holes for this problem. We have MATLAB solution for this problem. There you get the better picture. A minus B KD minus AD. So we can substitute the matrices here. Minus 1.7, this is the system matrix. 50, 260, 0.22, minus 1.4, minus 32, 0, 12. Minus, we have the B matrix as well. 272, 0, 14. And we have the feed forward gain matrix, KD1, KD2, KD3, okay? And we have finally minus AD matrix. So AD matrix also given us in the example, minus 10.1, 35, 150, 0.1, minus 1.1, 21, minus 21, and 0, minus 8. And after solving this matrix, we get the final expression 8.4 plus 272 KD1 15 plus 272 KD2 110 plus 272 KD3 0.12 minus 0.3 minus 1 minus 14 KD1 minus 14 KD2 minus 4 minus 14 KD3. Okay. So if you notice here, KD only affect the first and third row, right, in this matrix. Moreover, we can choose in this matrix the KD, KD1, KD2, KD3 in such a way that the first row of this matrix is 0. So from that condition, we can write KD 1 from the first row of the above matrix, we can find minus 8.4 divided by 272 KD2 minus 15 divided by 272 KD3 minus 110 divided by 272. Right. So finally, if you substitute these values in these rows and these rows, so anyways, this row will go to 0, but this row the last row will not have 0 terms. So let's find that. So now A minus BKD, here you can write, if we substitute all the values, I'm writing the final matrix 0, 0, 0. First row, it will satisfy with the above gains, and 0.12 minus 0.3 minus 11 and 0.43, 0.77, 1.7. And so let me rewrite the KD matrix also. KD matrix will have KD minus 8.4272 minus 15.272. This is vector matrix, something, no problem. 110, 272. Now we'll assume the same noise level, what is acting in the system. So we are going to consider same noise what we had in the last lecture. So XM we are assuming here, XM we are assuming 1 e to the power minus 5 minus 2 e to the power minus 6 and sine 100 t. So here 100 is the frequency, and also we are assuming the initial. Let us assume, since we are assuming the reference dynamics as in the form of dynamics, so this is a dynamics equation. So to get the in XD form, we should have, if you want to find the solution XD from this dynamic equation, we should have the initial condition. To solve any dynamic equation, we should have the initial condition. So let us assume initial target or initial reference signal target condition. We can write XD naught equal to 300. This is, we are assuming as a target condition. Okay. Now, BN already we had in the previous lecture. You already have the BN already found. Let's go back to the previous lecture there we have found. So Bn also we had, if you remember 0, 0 minus 0.0035, 0.004, 0.001, 0.0051, and C we had identity matrix 3 and D as equal to 0. So these are the values given to us. Now we'll go to the MATLAB part and we'll find. So I think we have found all the parameters what you require for simulation. For simulation of E dot dynamics, E dot. So we have all the values in this equation, right? We found this, and we also found this. Also, we are given this. So now, also we are given the XD also. So we can simply use the MATLAB command to find the error values, error dynamics. So we'll take the MATLAB result. So this is the MATLAB result for this particular problem. So I hope it is visible. So here, if you notice, we are having the system matrix. We have D matrix. We have E, D, E, F. AD is also given to us, and also we have the using DAM we can find P, and also theta P damping ratio and pole of the DGR dynamics, and this is the DGR eigenvalues, and which will help us to find the K control gains, and from this we can find the augmented matrix, and also we have the Kn, which is going to control the noise in the system, and here we are defining the Kd, which will be used to design as a feed-forward gain matrix, and this is the AD, and this is the matrix we just found. This is the this matrix, this one, this matrix. So it is here defined, and we have the KD parameter already had, and we are simulating the problem for 10 seconds with sampling time 0.01, and this is the noise level in the system, and this is the initial value of the this is the initial value. This is the initial value of the DCR dynamics. Now we can find this as a DCR system dynamics using these parameters. AD, zeros, I, and D, we can find the DCR dynamics. And so DCR dynamics, it is given to us, so no problem. Here we can find basically XD dot equal to AD XD, and here I is basically we are assuming C matrix, there is no control, so B is 0 0 and 3 0 matrix it is. So that's why B is not there, and I is we are assuming XT1, XT2, XT3 as the output of the DGR dynamics, and D part already assumed to be 0, right? So from this we can find this solution. Okay, this is the DGR dynamic solution. Now we'll come to the error dynamics. So these are the parameters going to use in the error dynamics, and this is the error dynamics we are having this CCL, closed loop error dynamics. And now we are finding error. So here E actually, here E is a vector. So E is actually E1, E2, E3. And this is other things are just to modify the plot. So if you notice in the plot, this is basically X1, acceleration. And this is the normal acceleration of the first floor. Second one is the second one. We had the pitch rate, and third the elevator aviation. Right. So, so this is how we can get the plot of this particular example. If you notice from the response, as time proceeds, we are getting the response is going to 0. After 10 seconds, it is converts to 0. So we can say that the effect of noise is not that much significant. And also we can track the desired dynamics, because all this plot actually, this is if you write here x1 actually our a minus, sorry, ad minus a, x2 actually qd minus q, and x3 actually ed d minus ed. So as time proceed, the error is going to 0. So it means system is going to converge to the desired dynamics. So this is how we can design the controller for to track the desired dynamics, and we have done for the longitudinal motion of the aircraft. This is very, very important example. And if you have similar kind of system to be designed, and if you want to see how the noise is going to behave or act in the system, you can design the controller and you can mitigate the noise. So I hope this is very important for designing the autopilot for aerospace systems. Okay, thank you very much. We'll continue from the next lecture. Thank you.